All right, thanks a lot. So this section will just get started, and feel free to stop me, Long Beach, when your food shows up. Also, Scott and Mark, if at any point you want to jump in and add to whatever I'm saying, please feel free to do so. Can everyone see my screen okay? Okay, so we're going to be covering a lot of ground here. Some of this is going to touch on other sections. It's a pretty comprehensive subject, and so we'll probably go a little bit faster through some of those things. But I want to start with a few fun facts, because at the end of the day, what we're dealing with in any high pressure system is stored energy. And there is usually a lot more of it in a pressure system than you might appreciate. So a standard decent sized industrial gas cylinder will hold the equivalent of about a pound of TNT. So that's some serious explosive potential there. Just ordinary compressed air from like a regular shop compressor can easily dislodge an eyeball from its socket. It can rupture an eardrum, or it can create hemorrhaging. 100 psi gas jet through a 1/8 inch diameter orifice. If that happens right at the surface of your skin, it can actually enter and inflate your flesh and even cause bubbles in the bloodstream, which can be incredibly painful, if not fatal. Even air under 40 psi from a hose can kick up debris. It can project metal chips around that can easily puncture your skin or your eyes. And if a hose does fail, it can whip around, and the hazard of that whipping hose can be pretty serious as well. So yeah, the goal of this this piece of the talk is to try to scare you guys a little bit and leave you with the impression that there are some real hazards here, and that there's a lot of energy that you need to be aware of. Now, the good news is that all of these are entirely possible to deal with, but you need to be aware of what they are, and so that's what we're trying to get across here. So in any high pressure system, you basically have two main categories of hazards that you're potentially going to face. One are the hazards presented by the fluids themselves. So you could have flammable agents, oxidizers, toxic chemicals potentially. You can have asphyxiants. If these things leak out, then you're going to have to deal with the results. Sometimes these fluids will also cause negative effects on the components in systems. They can corrode them, they can embrittle them, and so all of these hazards, due to the substances themselves, are going to be really important to bear in mind. But the other big piece of it is stored energy, and this is just intrinsic in any high pressure system, which is why we use high pressure systems, because they're good ways of storing and delivering energy. But there is a lot of energy there, particularly when a gas is compressed. Now, gas at a given pressure stores a great deal more energy than water or a non-compressible fluid does. So that's why, in hydraulic systems, pressures upwards of 6,000 psi are pretty common, whereas in a pneumatic system, that's like frighteningly high pressure. And so you need to be particularly careful when you're dealing with compressed gases, just because of that compressibility. There can also be other sources of energy apart from just that pressure energy. If you've got a fluid that's reactive, so nitrous oxide is a monopropellant, it can exothermically decompose on its own. Hydrogen peroxide can as well. On top of that, any fluid that is superheated, so if you've got cryogen that's under pressure and heated above its normal boiling point, or anything else, you've got the potential of a BLEVE, which was talked about a little bit earlier on, boiling liquid expanding vapor explosion. And the force of that fluid flashing into vapor as it's released can impart additional energy to an explosion. So all of these things are going to be really important to consider in any high pressure system that you're designing, and learning how to do this safely is really important. So one of the nice things about giving a talk on high pressure system safety is it gave me a great excuse to look through YouTube videos of things exploding and doing things that we hope will not happen to any of you guys. So we're going to see how well playing the videos over this works, but with compliments of YouTube, we've got a few useful cautionary tales.
When a typical cylinder is filled to its design pressure of 2400 psi, it will contain almost 300 cubic feet of atmospheric pressure gas, or about 160 times the internal volume of the cylinder. This compression of gas represents a tremendous amount of stored energy. If the outlet valve is broken off, the sudden release of compressed gas can turn the cylinder into a missile with energy to shoot through a cinder block wall. In one reported incident, a damaged cylinder penetrated 2 sheet metal walls before becoming airborne and exiting through the roof. The tank reached an altitude of 140 feet before falling back through the building's roof a second time. When a steel cylinder becomes a projectile, it can move with great force, at high speeds, and in unpredictable directions, with the potential to cause serious or fatal injuries.
So that's what can happen just with a totally ordinary high pressure gas cylinder. The Mythbusters also did a really good look at just what can happen if you shear the valve off of a high pressure gas cylinder.
High-pressure gas cylinders have been around for 100 years, and legends of their destructive potential have been around for 99. But could a ruptured tank really burrow through a brick wall? Into the next county.
Here we go, shearing the regulator off the tank. Attempt number 2. In 5, 4, cross your fingers, 3, 2, 1. Yeah! That's the sound! That is a lovely, lovely sound.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Oh, God. It was the Lord that did it.
At 40 miles per hour, the air tank turned the cinder block to cinders. It even put a fair dent in the wall 6 feet behind it.
Totally. I mean, it didn't go all the way through, but it went through this one, and it was working its way through that one.
I was ready to see this as not possible. I was totally expecting it not to actually work. This is one of those impossible tales. You know, we talked about heard the story, but no one knew anybody that it happened to.
You know, this was an optimum situation for this tank. What this tank did is as good as it gets.
My favorite thing is the perfect roundness of this console. It also pushed this entire wall back a half a minute.
Although the cylinder was deliberately aimed, you couldn't ask for a more convincing result. So let's call this myth totally and spectacularly confirmed.
And for one more look at what gas cylinders can do. Okay, so that's a little taste of just what can happen with compressed gas in a regular cylinder. I see it's about 1:45 right now. Did we want to do the break for food, or should we go on with Levees? Anyone? Long Beach?
Go ahead and do the BLEVE.
All right, BLEVE's coming up. Okay, so on top of just the energy in compressed gases, if you've got a fluid that has been superheated, you've got this whole added source of energy as it suddenly expands to ambient pressure. And the force of that happening can cause blast waves. It can help propel shrapnel. And this has actually occurred a number of times. And Mark mentioned one that he personally experienced. But in industrial context, this thing has happened as well. So as one example, someone at an industrial facility was using some regular carbon dioxide fire extinguishers. And one of these CO2 cylinders had about 5 kilograms of liquid carbon dioxide in it. And somebody threw it into a dumpster. So the dumpster was taken off to a scrapyard that put the contents of the dumpster through a shredder. So as soon as the shredder encountered the CO2 cylinder, it ruptured it, and the result was a carbon dioxide BLEVE. So the cylinder burst into a few fragments. You can see one of them at the bottom there. 1.9 kilo fragment of it flew all the way through a double-layered steel roof and landed 35 meters away. And this is just a regular CO2 fire extinguisher. One area in industry where you do sometimes see particularly dramatic BLEVEs is in things like propane and natural gas. These are generally stored under pressure, and they will definitely BLEVE if there's a fire or anything else that compromises the cylinder they're stored in. And here is a National Fire Prevention Agency video looking at BLEVEs and what they can do.
Analysis of experimental data and study of actual incidents have resulted in a clearer understanding of the mechanics of a BLEVE. While BLEVEs have been known to occur in tanks weakened by physical damage, such as from an accident, most BLEVEs result from fire exposure. When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly, with little warning.
Okay, so those are just a few examples of some of the very tangible hazards with high pressure systems. Now, here's another one that is maybe more directly relevant. So we obviously just saw what can happen if you've got a natural gas BLEVE, but what about something like liquid nitrogen? So this was an incident that actually happened at a university in the United States, involving an old LN2 cylinder. Now, first of all, on the picture on the left, we looked at spotting the safety hazards. What are some of the safety hazards associated with what you're seeing there? No PPE, very good. Yeah, he doesn't seem to be wearing any eye protection, and you can see a big cloud of venting nitrogen. So probably some eye protection would be in order there. Yeah, so there was this cylinder at a university, and it was being used on the second-story chemistry lab in the building. It was an older cylinder, and like any properly designed cylinder, it incorporated pressure relief devices, including a relief valve and a rupture disc.
Hey, Adam, can you wait? Our projector stopped working.
Oh, okay, projector issue, huh?
So how do we get it back to full?
You have to move the mouse around every once in a while, so the projector will shut itself down.
Our projector is back. You can keep going.
Okay, awesome. So this tank originally had a relief valve and a rupture disc to prevent overpressure, but at some point those devices had probably started leaking, and someone at the university decided to fix the leak by removing them and plugging them. Now, somehow it actually managed to carry on like that for quite some time before it finally did what you'd expect it to do. Probably people were withdrawing liquid from it fast enough that it didn't get a chance to quite build the pressure to a dangerous level, but eventually it did. So to set the stage here, the cylinder had been standing at one end of the lab, second floor of the chemistry building. The floor it was on was about 4 to 6 inches thick concrete covered in tile, and it happened to be directly over a reinforced concrete beam in the ceiling below it. So what happened with this? Well, it blew up, and specifically how it blew up. These were double-walled insulated cylinders. The inner tank started to expand as it yielded, and eventually it expanded to the point where it was in contact with the outer wall. That then constrained it so it could only expand on the ends. And it kept doing that until the bottom weld failed, and based on the accident report, they figured that happened at about 1200 psi. And the resulting explosion of this liquid nitrogen cylinder blew all the tile off the floor in a 5-foot radius around the tank, and it shattered the tile into shrapnel about the size of quarters, which embedded themselves in the walls and door of the lab. The door and the wall the door was attached to were blown completely out into the hallway. The remaining walls were all blown 4 to 8 inches off their foundations. Every window was blown out into the courtyard except for one that was already open. The blast cracked the concrete floor underneath it and shattered the supporting beam below that. Then, of course, after doing all that, the cylinder took off through the ceiling. The ceiling was also 4 to 6 inches of concrete, and it went right through it into the mechanical room above. Along the way, it hit a pair of 3-inch diameter water mains and drove them right up to the roof of the building, cracked the roof, and finally the cylinder stopped on the 3rd floor with a 20-inch diameter hole behind it. Fortunately, apparently this all happened after hours, so nobody was hurt as badly as could have easily happened. But apparently the next morning somebody noticed that water pressure in the building was a little bit low and went to check what was going on, and I imagine their reaction would have been pretty impressive. So that was what happens with an inert cryogen. What happens if the fluid is actually something reactive like liquid oxygen? Well, that happened as well. This particular story involved a couple guys who managed to salvage an old liquid oxygen dewar from a junkyard, and in their wisdom they decided to try to fill it. So they did, and they found that immediately it started venting out through the relief valve. So to solve that problem, they removed the relief valve and plugged it. And not surprisingly, that stopped the leak. So then they put their cylinder into the back of their truck, they loaded it completely, and took off down the interstate. Now, at this point, they got incredibly lucky. The truck got a flat tire. And so they pulled over and started working on changing the tire. So then a BLEVE occurred, and the picture at the top shows what used to be a pickup truck. It's not really recognizable as much of anything right now. Like with the liquid nitrogen cylinder, the dewar failed at the bottom weld. One of the 2 men was blown clean across 5 lanes of traffic. The other man flew about 40 feet in the other direction. The resulting blast wave of oxygen hitting the gas tank of the vehicle didn't react well. And so the results you can see there. The remainder of the cylinder took off like a rocket, literally, and returned to Earth about 400 meters away, where it plunged through the roof of an apartment building, annihilated the apartment underneath it, and severed a natural gas line. Once again, somehow nobody managed to get killed with this, but this is a really good example of what not to do, and also a good example of why these systems always come with overpressure protection. So that kind of sets the stage here. And what we're trying to do with this training is to make sure that you guys really understand the kinds of energies that we're dealing with in these types of systems. So this is all stuff that actually did happen. So once you know them, you can then take steps to avoid them, but it's important for you to know them. Now, as the obligatory disclaimer, we can't possibly cover every hazardous scenario in a weekend of training. There's always going to be things that will come up that are unique to your own particular systems. But we want to give you at least a flavor of the kinds of things that can happen and the sort of mindset that you need to approach these systems so that you can anticipate potential problems. But at the end of the day, you guys need to take responsibility for your safety and for your own actions. But we're here to help you guys in every way that we can. So let's start with looking at compressed gas cylinders, because they're going to be probably the most common source of pressurized fluid that you're likely to encounter. Long Beach, would this be a good place for a break before I jump into this?
Yeah, we're ready for a break.
Okay, sounds good.